start recording. Awesome. So the example that we didn't quite have time to do, again, I wrote this down, I posted it in the online notes. We're going to briefly go over it, and I'm really not going to go over it. The important thing here is kind of this u substitution. So since this is a loop, right, it starts and ends at the same place. If you were to do a u substitution here, u equals sine, du equals cosine, and you were to plug in the new bounds, you would get 0 to 0 for these bounds. And normally this is an issue. This is maybe a bad example to point this out on because you still get an answer of 0. But if you start at and end at the same place and you do a u substitution, you're going to get the same upper and lower bounds, which tells you it's 0. Unfortunately, this is an example that also gives you a 0, but it's not because the bounds in the u substitution would be the same. It's because when you go through and evaluate this, you get 0 minus 0, or you get stuff that cancels out. So this is a point for these flux, for these work integrals. Don't substitute the bounds if you do a substitution. Go back to the original variable, the original bounds, because this 0 to 2 pi keeps track of moving around the circle in a counterclockwise direction, whereas if you did sine of 0 and sine of 2 pi, again, that doesn't tell you anything. It tells you that you start and end at the same place, but it doesn't tell you what kind of motion, what kind of curve you're looking at there. I think maybe another example where this came into play was in class last week, actually. I think we had a similar integral. We didn't go through it. Sorry, not last week. It would have been before spring break, where you essentially have the same integral. You might have different bounds there, but we got a non-negative answer, or we got a non-zero answer. So again, this is something to pay attention to. Okay. Great. So we're not going to, really move away from this. It's a new module, but really in the book, we're in the same chapter. So this is section 16.3. Title is kind of a long one. It deals with path independence. I always screw up independence. I always want to write an A somewhere, but I think it's all E's. Path independence, potential functions. And potential is a keyword here, like an actual mathematical definition, much like normal is usually a mathematical definition, even though it doesn't really mean what it might mean in English. So we have those two objects and conservative vector fields. So conservative in the sense of like conservation of energy. We're trying to conserve something here. It's not necessarily energy, but it's that kind of idea. Okay, so 16.3. We're going to start off with an example. So we want to let our vector field equal xy comma x. We want to evaluate the work done by F from 0, 0 to 1, 0 along, first, we're going to look along the curve going from, or using the equation y equals x squared. And second, we're going to go along the curve C2 using the line y equals x. So we're going to see if or we're going to evaluate the work along two different curves and see if, you know, they're the same, they're different, and what's going on here. So I'm going to get my hand rest here real quick. All right. So let's do part one. Let's do curve one. The curve is y equals x squared, or this is how we want the curve to obey. And if we're writing out r of t, I know I mentioned this before the break, but let's just go through it again to remind ourselves. If we're writing out a curve and we're not given some explicit vector r of t, the way to sort of write this out is do r of blank, because maybe your variable will want to change depending on it. And always start out with a x comma y. And then we can do some sort of substitution. Maybe we want to use polar coordinates. Maybe we want to use some other type of coordinates, some other sort of substitutions to help us out here. So our curve is described by x comma y. And we want to use this equation, y equals x squared, to change this into a vector function with respect to one variable. Right? Well, y is equal to x squared. So one thing we can do is just substitute that in. Now, if I look at this vector, we have x squared. That's in terms of one variable. You can leave it as x if you want, or you could change it to t. You know, whatever your preference is, make sure you stay consistent with it. That's all I ask. So maybe we'll say r of t, or maybe I'll just leave that blank, and then down here we'll say r of t is t comma t squared. And this describes the curve C1 in general, but if we want to go from the point 0, 0 to 1, 0, sorry, that should be a 1, 1. My mistake. If we wanted to go from 0, 0 to 1, 0, then in this case, t should be in between 0 and 1. Okay, so we have our curve. We have our vector field f that we can replace with t and t squared. So f of r of t is equal to t cubed comma t. Once you get done with all the substitutions, right? You have x, y. So the work done in terms of C1, this is going to be an integral from 0 to 1. And we have the dot product of this vector field, t cubed comma t, dotted together with v of t. So I forgot to write out v of t. It's not too bad. Do that real quick. We get 1 comma 2t. So we're taking our vector field f and we're dotting it together with v of t. So overall, we get the integral from 0 to 1 of t cubed times 1 plus t times 2t. Again, we're going to skip the actual integration process of this. And I'll skip forward to just the number you get. This value should be 11/12. So again, it's positive. Context tells you that the vector field is kind of pushing you, you know, with this quantity overall. Okay, great. So we've done this work for curve 1. Now we want to do the same thing for curve 2. And I think I'll give you guys a few minutes to go through and work this out. So again, now for curve 2, which is given by y equals x, I want you guys to kind of repeat this process. Again, describe some r of t. Maybe I should have done an r1 of t and an r2 of t, and go through this whole thing. You don't have to evaluate the work integral if you have some time after you're done setting it up. Definitely go ahead and do that. But take a few minutes to go through. Okay. so let's go through this a little bit. Right, so we wanted, r of blank, start off with x comma y as the vector. And we want to use our equation or the knowledge from our problem in this part to, help us turn this vector into a vector of one variable, vector valued function of one variable. So y is equal to x, just substitute in the x, or y for x either way. But if we want to use t's, then we can say that r2 of t is equal to t comma t. Right, so we get that. We get our vector field f of r2 of t. Plug t's in everywhere. Remember, our vector field was x comma or x times y comma x. So we get a t squared comma t. We need the velocity vector in this case also. So we get 1 comma 1. And if we're thinking of this in terms of the m dy plus n dx, or sorry, m dx plus n dy, we can write these out. And so our integral work of C2, or long C2, again, our t bounds should be between 0 and 1, right? If we want to go from 0, 0 to 1, 1. So we have the integral from 0 to 1 of m dx, which is t squared times 1, plus n dy, which is t times 1, dt. It's another polynomial integral. We can go through this, but at the end of the day, you get 5/6. So the point of this all is that the work along either or each of these curves are not the same. So the vector field pushes you a little bit more along curve 1 than it would along curve 2. Now it's just by a small amount, but the point is these are different. This means the path matters. So what we're going to do for the rest of this section is examine, when does the path actually not matter? When does, giving 2 points and asking you to tell me what the work is done by the vector field between these 2 points, when does it not depend on the path? When is it always going to be the same, no matter, where you go? If you travel, a really long ways, you do a bunch of like little squigglies between this point and this point. Maybe you do some sort of path like this, or if you would do a path, straight through, when do these 2 curves yield the same amount of work done by the vector field? That's what we're going to look at. So if the path matters in this example, would the vector field not be conservative? Am I jumping ahead too much? You are jumping ahead too much. Yes, we will answer this question in good time. But yeah, we haven't even defined conservative, so let's hold back on the enthusiasm a little bit. But I like it. So yeah, let's check this out and maybe get to that definition of conservative vector fields. I guess before we move on, are there any questions about actually computing this work or going through this example up here? Okay, if there is, again, type it in chat. I'm gonna keep going for now. So this concept, just like in the title of the section, is called path independence. So when is this work integral independent of the path? Okay, so there is a very long definition, and I think we're actually going to write it all out. Right, this has been an inquisitive class that has cared about all the details. So let's definitely go through this. It's going to be a bit of writing, unfortunately. So we're going to let F be a vector field. Defined on an open region. We'll call that open region D in space. So this could be R2, R3. You know, again, we're kind of assuming it's an R2, but it doesn't have to be. Suppose that for all points A, comma B in this open region, the work, which is equal to the integral of C of F dr along a path C from A to B in D is the same over all paths from A to B. Okay, so this is our assumption, this long sentence, 2 sentences. So again, just to go over the assumption as you guys are still kind of maybe writing it down, we're taking a vector field which is defined on an open region. And suppose that for all points A and B in this region, the work along any path from A to B is the same. So again, it's kind of the picture I drew above. You know, depending on if we have a straight line to it or a really squiggly line or, you know, something else, we are assuming that the work is all the same in this case. So if this is our setup, then the integral, the work integral, is called path independent. This is the definition of path independent. In D, and we call the vector field conservative. On D. So I want to make this kind of extra clear here. What is path independent and what is conservative? So the integral is path independent, but the vector field is conservative. And again, this is in the case where it doesn't matter what path you take from points A to B, this vector field or this vector field is going to give you the same work done between A and B. So again, this is a large setup, but I really want to emphasize that the integral is path independent and the vector field is conservative. And these are, you know, if and only if they're equivalent statements, you know, this is what happens in this situation. So notation, actually, I don't care for this notation. Yeah, that notation isn't really useful. So this is the definition of conservative. It's also the definition of path independent. But we're going to look at another way to talk about a conservative vector field. So kind of jumping ahead. We're going to show that F is conservative if and only if, which means that it's equivalent. So this phrase here is equivalent to F being the gradient of some function. So conservative vector fields are exactly gradient vector fields. So these are one and the same. And we're going to show this. We're going to go into a little bit more details about this, but this is kind of sneak peek in where we're going. So keep this in mind. So again, this is a statement about the vector field. So to answer your question, so if the path matters in this example, the vector field would not be conservative. That's correct. Another definition, and this is getting to the second word in our, sorry, the second word, we've already defined the third word. So this is the last one we need to define. If F is a vector field on some open region D, and it just so happens that F is a gradient vector field, for some scalar function little f, then little f in this case. So again, we are starting with a vector field, and then we just so happen to be told that it's the gradient of some function. Okay. Then f, little f, is called a potential function. For the gradient of f. So again, it's not up. Potential kind of works in two different ways here. It's a technical definition, and potential kind of working with conservative sort of thing there. But it's also a potential function for f. So you can kind of put the emphasis on two different words here, and they both work, which is interesting. But one other careful thing that I want to point out here is I said it's a potential function. It's not the potential function. So what this kind of implies is that there may be many scalar functions which give you the same gradient vector field. And that is true, right? You're taking derivatives to get a gradient, so you're kind of killing off all the constants in this function little f. So there are potentially a lot of functions which give you the same gradient vector field. So these are a couple of things to be aware of here. Okay, so we've gone through a few definitions. We've gone through what path independence means for an integral. We've gone over what a conservative vector field as the definition is. We've gone over one way that we are going to start identifying conservative vector fields, and what this little f is. It's a potential function for the vector field. So These are 4 definitions that we want to be aware of here. Let's do an example. Or really, sorry, my notes are a little out of order. I think I still didn't put them in the correct order from earlier. I think that's right. Okay. So not an example. Sorry, we're doing another theorem. Let's F be some vector field, and we're going to give it the name Mn and P. And again, this is in the sense that F is a function of 3 variables, a vector valued function of 3 variables. So Mn and P are scalar valued functions of 3 variables. So we're going to let F be a vector field where M and P are just going to put in quotations nice. This means continuous, differentiable, all the things that we normally assume for functions in Calc 3. So they're continuous throughout an open connected region of D. This theorem is really what we're going to say is then F is conservative if and only if capital F is equal to gradient of little f for some little f. But we also have in this theorem that this integral, the work integral of the vector field along any curve, is path independent if and only if capital F is the gradient of some little f. So the idea here is that this, takes some proving to do. It's a theorem. It's not just like a nice lemma or fact. So here it is. And we need some assumptions. So sorry if today is a bit dry with definitions and theorems and stuff, but we do need to introduce this theory before we get into some of the examples. So some assumptions which we will sometimes take for granted. Sometimes we'll address these, but let's write them down at least. So all curves we will say are piecewise smooth. So for instance, when that last example for flux in section 6.3, it was kind of a half circle and then the line connecting the half circle here between these 2 points. This is piecewise smooth. So you can break this up into C1 and C2. C1 is the actual circle part and C2 is the straight line. This is a piecewise smooth curve because you can break it into 2 pieces and each piece is smooth. So that's an example of that. So that's one of our assumptions. Components of our vector field, so the Mn and P, have continuous first partial derivatives, first partials, right? This was the nice up above, or this is part of the nice up above. And the last thing that we're not going to look at very much is D is an open connected and simply connected. Region. So we know what open is, you kind of draw a dotted line around whatever region. This means one piece, right? So you don't have like a blob over here and a blob over here. You really want it to be one blob. And you don't even have a blob and kind of another blob. So like, right, one sort of idea is that if you had sort of like two circles, but you had a point here, we don't necessarily want this. And we don't want kind of a donut. So we really want just like an honest blob. Not like two blobs joined at a point, or or a blob with a hole in it. Like we want honest blobs here. So these are our assumptions. Sometimes they will come into play. A lot of the time they won't, but keep an eye on these if you see something about them on quizzes. Keep a eye out. These are the type of things that we might ask about on quizzes. So all of this leads to yet another theorem. Oh, sorry. So no straight lines in A. Sorry. So no, reading is sometimes hard. I'm sorry. So no straight lines like the A frame of a house. Sorry, I'm actually kind of confused. I know what an A-frame is, but my brain is not telling me what an A-frame is right now. Maybe, I mean, if I'm, is this what you're meaning? Right, something like this? Are you meaning something different? Can't have a shape with two straight lines that connect. You mean something like, I mean, like if this is our region, this is still fine. Right, it still doesn't have any holes. It's not really a blob, but it's like a rigid blob, I guess. But this is fine, right? It's still one connected piece. There's no holes in it. This is okay. I might still be misunderstanding, but things like this are okay. Yeah. If I'm still just completely missing the question, maybe let me know later, and we can talk about it, or post it in those discussions. That might be a nicer place for me to think about it a little bit more. So yeah, anyways, there's this theorem, which is the fundamental theorem. Of line integrals. That's the name of it. And again, we're gonna write this all out. So let's see. Be a smooth curve or path joining points A and B. This curve is going to, and these points are going to live in the plane or three-dimensional space. Let's see. Be parameterized by R of t. let f, little f in this case, be a differentiable function with a continuous gradient and we'll call that continuous gradient capital F. On a domain D containing C. Okay, so once we have all of this set up, we have a curve, we have 2 points, we have parameterization of a curve, we have a gradient vector field, we have all of this, then our lives become much easier. So just like the fundamental theorem of calculus in Calc 1, this fundamental theorem of line integrals says a very similar statement. Then if you wanted to evaluate this line integral, the work integral over f, or sorry, over c of f well, instead of taking the dot product, instead of going through all of this, you just take little f of b minus little f of a. Right. So just like part 1 of the fundamental theorem of calculus, instead of actually integrating this function, if you're given this little f, you can just go through and write out the difference between the endpoints. And again, there's something really to notice here. This is a conservative vector field, right? I didn't actually, I told you what C is, and I told you what the parameterization of C. So I picked a specific curve, but also it's a general curve. So, I picked it, but I really didn't. So what this means is, since capital F is the gradient of some potential function little f, this vector field is conservative. This integral is path independent. And so when you go to evaluate this integral, you have no mention of R of t, no mention of C, anything about that. You just have little f of b minus little f of a. So this is the power of path independence. This is the power of gradient vector fields. It's the power of conservative vector fields. And this is going to be the sweet spot where we're living in for the next little bit. So when you have a gradient vector field, at this point, you don't need to evaluate these work integrals anymore. You can just use this fundamental theorem. And it looks like we are about out of time. So we'll start with an example tomorrow. We'll go through and we'll see how to actually, we really don't. Let's just go seeing how to use it. So we take f equal to gradient of f for f of x, y, z equal to 1 over x squared plus y squared plus z squared. This is all the information that well, almost all the information. Then the work done by f from 100 to 002 is an integral. Again, we'll say a to b of our vector field dotted with dr dt. Don't really care what dr dt is. Don't care about a parameterization, because you can just say this is f of 002 minus f of 100 which is 1/4 minus 1, negative 3/4. That's it. So again, any path that you take, you may exert more energy as you go through, these different paths, but overall, the vector field is going to be pushing against you with a quantity of negative of 3/4, right? Overall, it's going to be pushing against you. There may be points where it pushes you very quickly or pushes against you, uh, makes it really difficult for you, but overall, you're going to get the same amount of help or hurt from this vector field. So we need a conservative vector field. We need a path independent integral, and this is how we compute it. So tomorrow we will, Friday we will go over more examples, talk about how to find potential functions, these little f's, and that's a bit of a trip. So stay tuned for that.